Hello chemists. In this video we're going to do three things. First, we're going to review a little bit what we talked about in our kinetics introduction and note a few important minor changes. And we'll finish our notes on kinetics and introduce a little bit about dynamic equilibrium, chemical equilibrium. First, we talked about the factors that influence the rate of reaction. One, we talked about concentration. The second one, a slight change for the nature of the reaction. So if you have a single bond versus a double or triple bond, how strong those reactions are, whether they're ionic or covalent, and also the state of matter that those are in, a gas versus a solid and a liquid, and the size of the particles are all important. Temperature, oh, we do have a cat sighting here. Yeah, gotta move the cat. Temperature, reaction mechanism, which I mentioned more in C block, but this would be, I use my morning routine. So like the steps in which a reaction takes place. For me, the time it takes to boil my water for my coffee is usually one of the slowest steps. And then after that, I am go for brushing my teeth and all that. And then whether there's a catalyst or not. So that is not why I have the cat on the video, but that is a coincidence that there is a catalyst that is certainly not speeding up this video. We talked a little bit about what a concentration versus time graph would look like for this reaction. And notice the important thing is the blue one, the NO2, the initial concentration of 0, that concentration is going up at twice the rate that the red one, the concentration of N2O4, is going down. That is because the coefficients, there's a 1 in front of N2O4 and a 2 in front of NO2. So every time one of the dinitrogen tetroxide decomposes, it's forming 2 of the nitrogen dioxide. So the concentrations change at different rates. And then, of course, once we pass this yellow line where the forward rate is equal to the reverse rate, we are in a situation called equilibrium. It doesn't mean the reaction is stopped. It just means that the forward and reaction rates, whatever they are, whether they're really fast or really slow, they're the same as each other. That's why their concentrations don't change. All right. So for collision theory, we said in order for us to consider whether a reaction leads to a product, a collision leads to a product depends on two things: the energy of the collisions, so that is both the mass and the velocity squared, kinetic energy of those collisions, and also the orientation of those molecules. I use the silly example where if you go to a dance and you're trying to find a significant other, if you are facing the wrong direction, like backing into someone, and you never look at them in the eyes, that is probably a lower chance for there to be a match. So the orientation of molecules when they collide in order to break bonds and form new bonds is really important. For activation energy, it's always a positive quantity. I'll talk about this down below a little bit. Fast reactions have a low energy of activation. That would be like something explosive. Slow reaction is something with a very high activation energy, like diamond turning into graphite. And the concentration and temperature of your reaction mixture does not change your activation energy. So that's one of those multiple choice questions that comes up, like what will change the energy of activation? So definitely not the concentration or the temperature, but a catalyst will. So a catalyst will lower the activation energy, and you can see in these diagrams below whether it's an endothermic or exothermic. This first one definitely being exothermic, and the second one being endothermic, because delta H equals positive. I showed both a non-catalyzed pathway in black and a catalyzed pathway in red. So there's our non-catalyzed, which has a higher activation energy, the one in green. And then lower activation energy in orange there, the lower amount of energy, the catalyzed pathway is always going to have a lower activation energy, which means you don't need as high of temperature or as high of concentration in order to get these things to happen. Okay, so those are two examples. And let's talk a little bit about this last thing. So qualitative effects of collision theory. So like what is going to increase the rate of reaction? So the size of the particle makes a big difference. And my best example for this is if I was trying to melt a bunch of ice. If I'm trying to melt a bunch of ice and I throw it into a pool, well, if I throw in a bunch of rabbit pellet ice, very small slushy ice, it will melt quite quickly because the surface of the ice, there's a lot of surface area exposed to the warmer water in the pool. So with smaller particle size, the rate of melting will be much higher. If I drop in like a giant statue of ice or a giant block of ice where there's less surface area overall, the rate will be much slower. It'll just have to melt from outside in, and the rate will be much slower. So the smaller the particle size, the more collisions you get, and the faster the reaction rate. For temperature, we can just think about popcorn. If we put it into a really, really hot oven or fire, I think it all makes sense that the popcorn will pop much faster. Yes, it'll burn, but that initial evaporation and popping will happen much higher at a higher temperature. Technically not a chemical reaction, but that's okay. Catalyst. We talked about dances. If that perfect song comes on with the perfect beat, the rate of people finding their perfect match is much, much higher. Where if it's a really slow song like Coldplay, maybe some people like that, or a really angry song like Metallica from the 90s, probably not the best song for matchmaking. So the right song you could think of as a catalyst. Another somewhat appropriate example, maybe somewhat inappropriate, is that if you have a club that is full of people, the chances of those people finding their perfect match would be higher. Where if you have a club of 2 people, the chance of finding your perfect match would be really, really low. So the higher the concentration of people, the higher rate of matchmaking or partnership. Okay, so that's it on kinetics for now. I want to talk just a little bit about chemical equilibrium and introduce it. Whenever you're asked, is this an equilibrium reaction or is something reversible, just look for these arrows. If you see a forward and a backwards arrow, that means this is a reversible reaction. So if you put a bunch of carbon dioxide bubbles next to water or bubble them through, some of those carbon dioxide bubbles will react with water to make carbonic acid, H2CO3. Likewise, if you just put a bunch of carbonic acid into water and let it go, carbon dioxide bubbles and water, but you'll see carbon dioxide bubbles come out. You see this all the time when you open up a soda. So a question came up is there a catalyst for this process? Is there a way to make this happen faster? Either carbon dioxide and water turning into carbonic acid or carbonic acid turning into carbon dioxide. And your soda water has a bunch of carbonic acid, but it only releases the bubbles really slowly. So if you've ever dropped one of those Mentos in, you can think of that as a catalyst, because the Mentos actually provides little sites, little spaces called nucleation sites, which allows the carbonic acid to break apart more quickly. So the Mentos you could think of as a catalyst that really speeds up this reaction. And that would work in both directions, by the way. So we only would really see bubbles coming out going in this direction, but it would also be faster going in the other way as well. So you guys can also think of a rechargeable battery in your phone. This is a reversible reaction. To get into the chemistry is a little complicated, but your lithium ion battery is definitely doing an electron exchange in that chemical reaction. That would be an example of our redox. Okay. Really, really important definition. a system at equilibrium has the same rate of forward and reverse reactions. So let me say that again. The forward and reverse reactions are happening at the same rate. It doesn't mean you have the same amount of reactants and products, and it doesn't mean that the reaction has stopped. It just means that the forward and reverse rates are the same, whether they're really fast or really slow. All right, the concentrations of those products therefore remain constant because the rate at which you're making a product is exactly the same that you're making a reactant. You can think about it like students at Sage. We have about 540 students. Does that mean we always have the same 540 students at Sage? No. The rate of seniors graduating is about the same as the rate of freshmen coming in. So it keeps a pretty constant rate. So there's another example. Okay, so looking at an example we talked about before is if we start this situation N2O4 and NO2 with different concentrations, we're going to see different ways to reach equilibrium. In figure A, we're starting entirely with NO2, this guy. So the reaction vessel only contains NO2, and the reason I know that is because its concentration is way up here and the other one is 0. In figure B, the reaction vessel only contains N2O4 and the other one is at 0. In figure C, it looks like we're starting with a little bit more N2O4 and NO2. So we have both. But in all three of these cases, we still reach equilibrium. And even though the concentrations are going to be different in every case, they still remain constant once they pass this point where the forward and reverse reactions are the same. Equilibrium is reached, but at equilibrium, the concentration of each substance is not the same. We talked about Catalina population versus California mainland. We have roughly the same population of each, even though that changes on like holiday weekends. So even though we have different people on Catalina all the time, different groups of people visiting and living there and moving back, they remain, I think we said somewhere around 40 million for California. And then for Catalina, we said roughly 5,000. I have no idea if that's right. But if 250 people get on a boat to go to the mainland, at some other point, maybe 250 or so will go back to Catalina to keep that 5,000 people, and the population's pretty constant. All right, the last thing we're going to cover in this video is how to write an equilibrium expression. There are no constants, and it might say Kc, it might say just K, it might say Keq, it might say Ka, it could say Kb, and it could say Kp. There are a whole bunch of different Ks. For C, this means it has to do with concentration. For EQ, this means, well, it has to do with equilibrium. For A, that means acid, and really it doesn't matter. They're just to help give us more information. B, you might guess, is base, and P is for gases, for pressure. But they all mean the same thing. They all mean products, concentration of products over concentration of reactants. And that's an oversimplification. So K is always some version of concentration of products over concentration of reactants. And if we have an equilibrium, arrows like this, it tells us that we're going to take our product C, whatever its concentration is, we're going to raise it to the power of its coefficient. So we'll do a little c up here. And then we multiply that by the concentration of D and raise it to the power of its coefficient. A fancy term for this is the law of mass action. For the reactants, we're going to do concentration of A, and you guessed it, a little a is the power, concentration of B, and little b is the power. When we plug in all these concentrations and coefficients, if we happen to know them all, we're going to get a number with no units. And these are only taken at equilibrium in this case. Not like your starting concentration or not your initial. For pure liquids or solids, we say the amount consumed is very low, or the concentrations are so low that they stay constant. The amount that's used is constant. So they are not included in this equilibrium expression. So liquids and solids are never included in this. So only gases and aqueous. So gas and aqueous only. That's really important when you're asked to do this. So they're not included in the equilibrium expression. And this number you're going to get is either going to equal 1, which is rare, which means you have about the same amount of products and reactants. If you get a number much bigger than 1, that means you have a lot more products at equilibrium. If you get a number which has a lot more reactants, if you have a lot more reactants at equilibrium, you'll get a number less than 1. So if we have K equal to 1, so we have about equal products and reactants. And then K greater than 1, that means we're going to have products greater than reactants at equilibrium. And then K less than 1, we're going to have products less than reactants, or more reactants at equilibrium. So if you go back up to these graphs really quick, notice that we would have more reactants than products in all of these. So our equilibrium constant, not surprisingly here, is going to be less than 1 because we have more reactants than products at equilibrium. More N2O4 than NO2. Oh, I already have that down here. And we're not going to do that. So greater than 1, products are favored. Reactants are favored. So that means it's a more forward reaction, and this is a more reverse reaction. Okay, that's good for now. We'll pick up on the example when we get to class next, and I hope that helps. See you next time.